Okay, today we are going to discuss about support vector machines. This is also another form of machine learning algorithms that we are going to learn, which is somewhat different from the earlier uh, versions of machine learning algorithms that we have learned, mainly related to linear regression, logistic regression, and so on. Because this is kind of non-linear and it is kind of bit different compared to the other algorithms which were using gradient descent algorithm for its optimization. But when it comes to support vector machines, the algorithm that is used for optimization is not that explained in today's lesson because its theory is far beyond our scope of learning. So actually, in most of the when it comes to most of the content of support vector machines, its internals and their proofs, uh, we are not going to discuss about those things because they are bit highly mathematical compared to our scope. So we are not going to discuss about the mathematical proofs that much. But when we are discussing about support vector machines, we will have to discuss some of the mathematics and their optimization algorithms little as possible, which is mandatory when we want to learn about support vector machines. Right? So let's start from the problem what we have. Right. So in support vector machines, this is mainly used at the beginning, especially for classification problems. Right? And later it was used for regression problems as well, but we are not going deeper into the regression problems that can be solved with support vector regression. But we will discuss mostly about in this lesson about support vector machines, which is about a classification problem, right? When it comes to support vector machines, it is mainly a binary classification problem which we are going to solve. So compared to the logistic regression where you can use softmax classifiers and so on, there is no uh, native uh, multi-class classification technique other than one-to-one and one-to-many techniques. Therefore, we are limiting for binary classification. Right? So before you start about classification, just remember what is classification. Right? Suppose you have, for example, two variables, x1 and x2, and when we have a data set where there are positive and negative data points, and if we want to classify these two types of positive and negative data points using a machine learning algorithm, what we call it as a uh, binary classification problem, right? Because we want to classify these two into two classes where there are only two classes, right? So that is why we call it as binary, right? Because we want to classify either one of them. It is a classification problem, right? Uh, and also when we were using uh, linear class bound decision boundary, right? So this can be a single line, straight line if it is a two-dimensional problem, like if there are only uh, two variables, it may be the case, but when there are multiple uh, dimensions, it may be a linear hyperplane, right? So we have learned about linear hyperplanes where the dimensions of the linear hyperplane is 1 minus the total number of dimensions in this vector space, right? For example, if in simple terms, if there are because in this case we are looking at a two-dimensional vector space, so there are this is one dimension x1 and the other dimension is x2, right? because of that, there are two dimensions. So then the decision boundary has only a single dimension, which is this. There are two minus one, right? There's only one dimension in the when it comes to the decision boundary. But when we have three dimensions, then it would be a two-dimensional hyperplane or flat plane, two-dimensional plane, which is separating these two classes. Right? So this decision boundary can be described by this kind of a linear equation, because this is a two-dimensional one where there are only x variables and y variable, sorry, x1 variable and x2 variable. So actually, there's a this third variable is there, but when it we are looking from top, we can see there are only x1 and x2, right? So this is the equation for the decision boundary, is represented by this yellow line, right? So if all the data points uh, that are having y positive, that means all the data points that are at this side will be having y value greater than 0, right? In this side, all the points will be having y value negative, right? That is how you classify these two classes using this linear decision boundary. When it comes to linear regression and logistic regression, we were discussing about the parameters that are used, right? Mainly we were describing the parameters as the beta vector, right? For the coefficients of parameters, where the beta vector can have beta 0, beta 1, beta 2, and beta n up to beta n. And this beta vector is represented in somewhat different way when it comes to support vector machines, right? So instead of using beta 0 to beta n as beta, we will have two values, which is beta 0, we call it as b, and from beta 1 to beta n, we call it as w, capital W vector, right? So simple b will be a scalar value, which is equal to beta 0, and capital W will be a vector, which is uh, sorry, should be a vector uh, which is corresponding to beta 1, beta 2, and beta n values, right? That is what it says. So from here onwards, when we say b and w, when we say b, it is about the coefficient intercept, right, or the beta 0. W are the rest of W represents the other coefficients of the parameters, right? Coefficients which are the parameters of the model. So first, let's see what is this support vector machine, which is used for classification, right? In this case, we are using a similar kind of linear decision boundary, which is also which a flat one or a linear hyperplane when it comes to multiple dimensions. And when it comes to SVM, also we can have a similar kind of representation where this linear equation can be represented like with this WT W transpose times X plus B equals 0, which is the vectorized format. Right? So this is the like in the logistic regression case, this is the support vector machine decision boundary. Right? So similar to the logistic regression, when we want to separate these two classes, we are using this decision boundary. And the only difference is that there are two types. So before that, so let's say that there are two types of support vector machines, right? So first we are going to discuss about the hard SVMs or hard support vector machines, where we are assuming that all the uh, data points are linearly separable. Right? Linearly separable means with a linear decision boundary, we can separate these two classes. If all the data points are linearly separable, that means there is no any data point that is classified incorrectly when we are using this decision boundary, this linear decision boundary. This is known as a hard support vector machine. Right? So this is actually a much simpler case, specific case for support vector machines, right? Because when it comes when it comes to real world data sets, sometimes we find there are some data points that are uh, misclassified using this decision boundary, right? In this case, hard SVMs may not be used, but for the study of in the theoretical way, we have to start with hard support vector machines, where we assume that all the data points are. We take some example where the data points are can be 100% classified correctly using a decision boundary. Right? So the idea of this support vector machine algorithm is to optimize for this linear decision boundary, or find this linear decision boundary uh, so that we can classify these two classes, right? So when it comes to logistic regression also, we wanted to find the parameters related to this decision boundary, right? Similarly, with support vector machines also, we are going to find the parameters in this decision boundary, which are b, w1, w2, or simply w vector and b scalar, right? These are the values that we are going to find by running this support vector machine learning algorithm, right? But there are some difference between the support vector machines and support vector machine classifier and most of the other machine learning algorithms. The idea of support vector machines is that in support vector machines, they are just looking at the boundary. Right? You are just looking at the data points that are only very close to the boundary, right? We don't care all the other data points that are away from the boundary, right? So what we want is to make this classifier, right? So in this case, we are discussing about hard SVMs, where we assume that the data points are linearly separable. That means we can use this linear decision boundaries, and we can uh, classify all the data points with 100% accuracy. Right? So in this case, we are using this hard SVM, where we are going to find find the values for these uh, for these w and b values. So we are going to find we are going to we are having concern about only about these values that are very close to the decision boundary, right? So this is so around this hyperplane, we are having a band, right? So which is equally distance from this hyperplane, right? So in simple terms, if we say this is just a plane, so uh, there's a band, upper band and lower band, that, or some two bands that are running in the either sides of this hyperplane, right? With the equal distance, right? So all these two boundaries, these two bands are equally distance, are located equally distance, known as W distance, right? From the from this decision boundary. That is how we define this support vector machines. So the idea of finding this decision boundary, so that we want to find this decision boundary where the distance between this decision boundary and these close data points are minimized, are maximized, right? So first we want to have the minimum decision boundary, and we want to draw this hyperplane so that this hyperplane is distant as much as possible from the closest data point, right? So there are two things that we have to think about, in other words, right? Where we have to find a hyperplane where these two classes are classified as much as possible, right? So in the hard SVM, we are classifying them in the 100%, right? With 100% accuracy. And we are concerned about the data points that are very close to this boundary, right? So we call them as support vectors, right? So we want to draw this line so that the distance from each of these data points from this decision boundary are maximized, right? So aren't you, if you aren't sure, so let me explain it again, right? What we are trying to do is we are trying to find the hyperplane, or find the hyperplane means we are trying to find W and B values, maximizing the minimum distance. The minimum distance means these values, right? Right? From hyperplane to its nearest data points, right? So once you find this decision boundary, the closest data points, or which are also known as support vectors, will be having an equal distance from this decision boundary to the support vectors, right? So in this case, now what you understand is we are only concerned about the support vectors, right? Once you find these support vectors, you don't have to think about the remaining vectors or the remaining data points, right? Which are away from the decision boundary, that are far away from the support vectors, right? So that is the beauty of this support vector machine algorithm, right? You are only concerned about the most critical data points which are affecting our classification problem, right? Not the other data points, because when these data points are satisfied, all the other data points are automatically satisfied, right? So whether we add more data points or remove data points from either side is not a big problem. What we are concerned, or our problem is finding this decision boundary by maximizing this distance from the decision boundary with the support vectors, right? In order to simplify this process, we generally take the Euclidean norm of the W vector, and then we divide them by these distances. So we will get instead of W, we get 1, and so on, and the margin, which is the 2 times W, will become 2, right? So this is how we can simplify. And now let's move into the problem or the mathematical representation of the this support vector machines, right? So when it comes to the support vector machine optimization problem, This optimization cannot be done with optimization like gradient descent optimization. Right? There's a special type of optimization we are not going to discuss in this lesson, right? But what we are going to discuss about the problem which we are going to optimize. Right? So the same problem which we are going to optimize with support vector machine uh, can be explained in two different ways. Right? So one is known as the primal problem, the other one is known as the dual problem. Right? The same problem, but we explain it in two different ways for different reasons. We will explain why we are doing it. Right? First, let's think about the primal problem. Right? So this is also known as the geometric problem. Right? Where we can visualize how visualize means we can intuitively we can think why this is correct, right? Why this primal problem is correct, because in the Cartesian plane we can draw it and we can have some understanding, right? What is this problem, right? So what which we are going to solve. So when it comes to support vector machines, this is what we are going to solve. Right? We are going to minimize half of w's norm square plus capital C times addition of psi i's, right? So we will see what each of these parameters means. Right? So we know this W is the uh, norm, right? So we will see what it is going to say, right? So, and this C is actually a hyperparameter which we are going to define, right? We have to take, and this psi I is also a form of uh, variable which is known as slack variable. So we will see what it as well. Right? So what we are going to do is basically we are going to in order to find this find the solution for this support vector machine, or find in the values for W and B, or in other words find in the decision boundary, what we are going to do is we are going to minimize this function, this relationship subject to yi w transpose xi plus b, which is greater than or equal to 1 minus psi I, where I is 1 to n, where psi I is a positive or 0 value, right? So this may sounds a bit mathematical, but once we look at each of this component, we will understand what this really means, right? So this problem is known as geometric problem, or the primal problem, and this is what it means, right? So in this W norm terms, what it says is that it is the Euclidean norm of the weight vector, right? So this is the weight vector which we are going to find, right? So what we are going to do is we take the Euclidean norm of this vector, and that is what is known as this this W norm, right? So this is the same W norm is in the this minimization value, right? And the earlier case we were describing about the hard SVMs where there are no misclassifications, right? But I said that in real world, not all the data points can be classified with 100% accuracy. That means with the linear decision boundary, we can't make sure that you can classify all the data points. Sometimes there can be misclassification when it comes to natural data sets. That is how it happens, right? So when it comes to natural data sets, we are going to find some find the decision boundary where we are trying to maximize the accuracy, but we are not going to achieve 100% accuracy, right? As I always said, with machine learning, we are just trying to approximate the nature. Right? In this case, what we are going to do is we are going to uh, find better optimization values for SVMs, but by minimizing the misclassifications. Right? So in these kind of support vector machines are known as soft SVMs, where we don't assume very hard assumptions like all the data points can be classified with 100% accuracy, but there can be misclassifications in soft SVMs. Right? So with soft SVMs, we have to use this psi I slack variable. Right? So for each of the psi I values are used for each of the data points for representing the slack value or the values that can have due to misclassification. Right? For the moment, that's just what you have to keep in mind. In this statement, the capital C is, as I said, which is a hyperparameter, is actually a regularization parameter that you have to select. Right? So when it comes to a hyperparameter, we have to set that value by our knowledge, or we have to do it several times and find a good value for the hyperparameters, right? So this is a similar kind of hyperparameter known as the regularization parameter, which adds some sort of regularization into this optimization problem. This actually can be somewhat analogous to L1 regularization, right? So the goal of this this optimization problem is to minimize this objective function, right? We are trying to minimize this objective function while ensuring that all the data points are correctly classified. But sometimes when they are not classified, we are taking the margin of at least 1 minus psi I, right? So that is why we take this psi I, because in this case we can't assume that all these values are higher than 1. Because of that, we have to use this slack variable so that this condition is satisfied. Right? Slack variable is compromising the accuracy of the model for making it possible with soft SVM. Right? For becoming a hardware SVM to soft SVM, we have to use this 5 variables. By trying to minimize this W norm, what we mathematically try to minimize is minimize the distance between the solution hyperplane and support vector. Right? Actually, what we are not going to do is we are not going to minimize W, but what we are actually going to minimize is this distance too. Right? So we are going to reduce this distance so that we are going to reduce this distance and we are going to maximize that this lane, that means the two-way lane which is around this decision boundary. That is what we are going to do, right? That is what we are. So in mathematically we can say that we are trying to minimize W norm, and that is what we are really doing. We are trying to find, we are trying to get the support vector values, and we are going to find the decision boundary where the distance from each of these support vectors is maximized, right? And we said that this is the constraint part, right? So when it comes to this subject to this one, so if you don't if you ignore this slack variable, this is the constraint, right? So if we take only this one, what we are trying to do is we are trying to maintain at least a unit distance between the hyperplane and its nearest vectors. So this is the scenario, right? So we are trying to keep at least a distance of 1 from the hyperplane. That means for all the data points, we have to have at least 1 distance from the hyperplane. That is what we are trying to do with this constraint, right? So this satisfying this constraint will become problem only for the support vectors, right? So because support vectors are the nearest vectors that are affecting critically for optimizing this problem, right? So we will say that once we come to the solutions, we are only thinking about the support vectors. That is why this is known as support vector machines, because once we find the support vectors, it is the end of the game. We are done, right? So unlike in the other machine learning algorithms like linear regression, we have linear regression or logistic regression, where we have to consider all the data points. With support vector machines, we don't have to think about the other data points. So this is very useful when it comes to non-linear decision boundaries, not decision boundaries, but when it comes to non-linear data, right? That means if the data are not distributed, data are distributed in a very weird way, right? So like there's a high class imbalance, and there are some non-linear way of data distributions. You can use these support vectors without much issues, because in this case we are just considering about support vectors which are only closer to the decision boundary, right? The only problem is that when we are using support vectors, we are assuming the main assumption is that the data can be classified with this decision boundary, right? Especially this linear decision boundary up to now, right? So in the future, we will see how we can use non-linear decision boundaries as well. For the moment, if you say that if you can linear separable, that means you can separate these classes with linear boundary. That are the cases that we are going to consider. But there can be some misclassifications, and in order to allow these misclassifications, we use the select variables, which is converting an hard SVM to a soft SVM, right? So in these constraints, right, uh, these psi i's, right, is used so that this for the data points that cannot maintain this distance, right? So that is when we are using this psi I variable. So this is a hard SVM. What you see is a hard SVM, but in the real world there can be some misclassifications where these data points cannot, where these misclassifications are not satisfying this distance of 1. So that is why when we are using this select variable. So and then we have to think about this C or C have a parameter which is known as the regularization parameter. Right? So when you are finding a value for this regularization parameter, you have to think about its trade-offs. Right? So it is a variable that can tune in between maximizing the margin and minimizing the classification errors. Right? Something like this. Yeah. When you use a low value for C variable, this is a simple C, but it's actually a capital C. Right? When you are using a low value of C, you can maintain a large decision boundary, right? But there can be misclassifications when we are using low C values. When you are using larger C values, you will have less misclassifications. In this case, there are no misclassifications, right? But the problem is the decision boundary is very small, right? So in this case, the decision boundary is very wide. Because of that, when it comes to the unseen data, right, in the test data set, uh, we can assume that this kind of model would be very robust at real world data. But when it comes to this kind of, but the problem with this kind of C value is that there can be errors. That means this would have a higher bias. But because uh, this may be much more reliable with unseen data, so this can be less in variance, right? But when it comes to larger C, larger C values, there can be very lesser amount of misclassifications. But in the downside, we will have a smaller or narrower decision boundary difference, right? Because of that, there can be, so this kind of decision boundary would be subjected to higher number of misclassifications when it comes to unseen data, right? Uh, because of that, this when it comes to test data, the error number would be higher when it comes to these kind of larger C values, right? It is like the higher variance problem, right? Where your data would be overfitting for this training data set, but uh, it would be having a very lesser accuracy when it comes to the test data sets, right? So this would be having a higher variance, low bias case, where this would be a high bias, low variance case in some way, right? So that is what we can do with tuning the C variable, right? So you can with trial and error or with some attempts, you can find the best value for C, right? Okay, now let's see what can we do with nonlinear decision boundaries, right? So we said that uh, with slack variables, we can uh, make it enable to use support vector machines, even in the cases where there can be misclassifications, right? Using the slack variable. So with soft SVMs, with slack variables, you can have we can have approximate models even with misclassifications. And we can use the C to uh, tune the bias variance kind of relationship, right? But when it comes to some types of uh, data sets like these kind of data points, where all the red colors values are belonging to one class and blue color values are belonging to another class, or these are negative class and these are positive class. These points are belonging to the positive class and these belong to the negative class. So in this kind of scenario, it is not linearly separable, right? That means you can't use a straight line, and it would not be possible to uh, classify these two classes in whatever the manner, right? Because this is actually not a linearly separable case. Even with any amount of slack variable values or with C values tuning, you can't do it, because uh, this is basically not a linearly separable case, right? These two classes can only be separated with if we are using a circular decision boundary like this, right? Like this yellow boundary, right? So this is a very non-linear class boundary where you can't use a linear decision boundary at all, right? So as we have discussed in logistic regression, when you have these kind of issues, what can we do is we can use you can convert this uh, representation, which is at the moment is having a two-dimensional case, by adding more dimensions, right? You can actually transform this classification problem into a linearly separable situation, right? For example, you can say that when it comes to this decision boundary, you can see this the circular decision boundary be something like this, right? Where you are using the squares of x1 and squares of x2, right? It should be having multiple dimensions if we are using these kind of uh, squares, but you can't use it in this 2D space, right? So when you add more dimensions into this the vector space, right? So in this two-dimensional case, you can't classify it with the linear decision boundary, but when you add another dimension, right, you can see using this third dimension, you can use this decision surface or decision plane, and you can classify these two classes into two different classes easily, right? Similarly, we can use sorry, similarly you can add, if when you add more dimensions, or when you are creating more and more dimensions into the vector space, there's a possibility that you can classify these data points into uh, different classes, right? Using a linear hyperplane, right? With circular hyperplane, you can already do it, but because we are using a linear hyperplane in this support vector machines, we have to transform it into multiple dimensions, and then only you can convert it, right? But the problem is when you are increasing the dimensions, uh, there are several problems, right? So the first problem is that it is computationally getting expensive, because when you increase the number of dimensions, the computational cost is exponentially increasing with the number of dimensions. The other problem is that when it comes to calculations, it would not. So this computation problem uh, becomes expensive, right? Like we see it in the mathematical way also, it is difficult to explain it with this primal problem, how to convert it into multiple dimensions and do it, right? You can add several dimensions and do it, but it would not be scalable, right? So because of that, there's a better way to do this, solve this support vector machines, by converting this primal problem into another form of problem known as the dual problem, right? So it is like we are explaining the same mathematical problem in a different way, right? The primal problem is a form of explaining the optimization in a problem in a certain way, which is actually much intuitive in a geometric sense, right? Uh, where we have used to explain how it should be there in the Cartesian space. But in the dual space, it would not be easy to explain in the geometric space, but the mathematical, the computation wise, it would be much cheaper, right? So let's see why we are using this dual problem instead of using the primal problem. And so we are not going to prove why it is much efficient, but we are just going to learn that it can be used for when we are having multiple dimensions. We want to have multiple dimensions, right? And this is it, right? So this dual problem is also known as the functional problem, right? Where the optimization problem is converted into a new form like this, right? In this case, we are going to maximize this statement, right? Here you can say there are alpha values, which are known as Lagrange multipliers, right? where this I and y, I and j are relevant to two different data points, right? Where you have two y values, two x values, and so on, two alpha values. And the idea of this dual problem is this is equivalent to the primal problem. And if we can convert the primal problem into this form, and if we can optimize it under these constraints, right? Yeah, the alpha I is between 0 and c value, all the I values, and when the alpha I yi summation is equal to 0, we can find the values for these alpha values, right? So the values that we are going to find by optimizing this statement is the get the values for these alpha values, right? Which are known as the Lagrangian multiplier. So we are not going to discuss how these uh, this mathematical uh, formulation has happened, right? So how that the primal problem was converted into this dual problem. But what we are going to see is how this dual problem is going to be used for the optimization easier than the primal problem when it comes to uh, dimensionality increasing. Increase is required, right? So the idea of having alpha I values is that when you have these alpha I values or the Lagrangian multipliers, uh, once we find these alpha I values, uh, most of these alpha I values would be zero, uh, right? But there would be some alpha I values which would be positive, which are relevant to the support vectors. And once we find these alpha I values, we can find the support vectors relevant to each of these alpha i's, right? So these alpha is actually relevant to each of the data points, right? So some of the alpha i's will be positive, which are relevant to the support vectors, and only these alpha using these alpha I values, we can find the support vectors, right? Once you find the support vectors, we can find the decision boundary, right? So in support vector machines, we say that when we are deciding our hyperplane or the decision boundary, we are only concerned about the support vectors, right? So if we can find the support vectors, then we can find the hyperplane, right? So by optimizing into this statement and subjected to these constraints, you can find the alpha I values that which are positive, which are relevant to the support vectors, and using these using these alpha I values, you can find the exact support vectors, and from the support vectors, you can find the decision boundary or the hyperplane. This is the objective of this problem, right? So the objective of the function is to objective of this problem is to find the decision boundary, right? So once you find the decision boundary, the problem is over, right? Machine learning problem is solved. So when it comes to this dual problem, we will only have to find alpha I values that are relevant to support vectors. Number of actually this when it comes to support vectors, there would be very few number of support vectors in the data set, right? So because most of the data points are not support vectors, uh, which are away from the decision boundary. Right? There are only very few support vectors. So finding these values is not after you find these values, it would not be that much computationally expensive compared to finding the W and B values uh, or the weights values and these intercept values in the primal problem, right? So in the primal problem, we said that we want to find W and B values for the weight vectors, right, and the intercept. But if you were going to do that for all the data points, we would have to calculate this W and B values for all the data points, which would be very expensive when it comes to computation. But if we find only the alpha values, we would only have to find the alpha values for the positive alpha values, which are relevant to support vectors. In this case, you don't have to, you would have lesser amount of computation to be done, right? And in this, and there's another advantage of using this dual problem, which is relevant to this multiplier, right? So we will discuss what is this later. In this case, we find that two data points are used as vectors, and they are multiplied like in the dot product, right? Xi transpose times xj, right? Here what we do is we are this term can be used for a technique known as kernel trick, so that you can use this kernel trick to for automatically converting these dimensions into many number of dimensions, even to infinite number of dimensions, without much computation, right? And get the effect of dimensionality increase, so that you can have the linear separability, right? And you can separate these classes without actually converting them into higher dimensions, right? So this is known as the kernel trick. So we will see how this kernel trick is used using these two, using this multiplier, right? So this kernel trick is used especially when these decision boundaries are non-linear. That means when they are not linearly separable, then we would have to use a non-linear decision boundary. In these kind of cases, we can use this kernel trick where it would automatically convert this few dimensional data set into multiple dimensions. In the multiple dimensions, it would automatically classify them with the linear decision boundary. So the machine learning problem, SVM problem, would be solved with very high accuracy, like we have used the nonlinear decision boundary, right? So this can be achieved with this kernel trick. So we will see what is how to use a kernel trick in later slides, right? So this is what it says, right? First we find the alpha i's for support vectors that are greater than 0, right? So this is about dual problem, right? So when you use the dual problem, we find the alpha I values which are greater than 0, which are relevant to the support vectors, right? And using this formula, you can find the W vector, right? So this sum of S means for all the support vectors, we add these alpha I, yi, and xi values, and then you can get the W value, right? And you can get, this is a matrix, this is a vector, right? And this B value or the bias can be calculated by using a single, by substituting it into a substituting a single support vector into this formula, right? Where the B is yi, so we can take a single support vector and take its yi value minus wt value, which was already calculated, and the xi value of this support vector. With this value, we can calculate the B value. So in this way, we can calculate the W and B values for the in the primal problem, and the problem would get solved, right? So that is how you calculate it. And you can make predictions using this formula, where you can take this WTX plus b, and we can take the sign of it. If this one is positive, those are positive values. If it is negative, so this if this uh, value is negative, it would be negative class, right? It would belong to the negative class. Otherwise, it would, if these values are positive in sign, so the sign is a function which finds the sign of whether positive or negative of this value. If it is positive, it would be classified as the positive class. Uh, Otherwise, it would be the negative class, right? This is how the uh, hypothesis function or the solution function looks like, right? Okay, now let's see how this transformation to the high dimensionalities happen. So first, let's see what we mean by converting this into higher dimensions. Right? For example, if you say that now there are two features, right, for two variables, and we convert it into three variables by defining the new x3 by a formula something like this, x1 square plus x2 square. So we can define x3 as the new variable, and using these three variables, we may be able to with now there are three dimensions. With these three dimensions, you can make the data set linearly separable, right? Sometimes, right? When you increase the number of dimensions more and more, there would be higher possibility of separating the data set or into using a uh, linear decision boundary, right? So in other words, in simple terms, you can, when you increase the dimensionality, the possibility of linear separability would be increased, right? So because of that, because the SVMs can only be used for linear separable cases, if we can increase the number of dimensions, and if it becomes possible to be classified in multiple dimensions, this SVM can be used for nonlinear decision boundaries as well. So initially it was a nonlinear decision boundary, but after converting, by after adding new variables like this with higher order polynomials, uh, now the dataset would be linearly separable with higher number of dimensions like x1, x2, and x3. And now the SVM can be used because it is linearly separable with a new number of uh, dimensions. And now the SVM can be solved by classifying into two different classes, right? But the problem is when it comes to increasing the number of dimensions like this, right? The computational that is required would be increasing exponentially with the number of variables, right? For example, if you add, for example, it may become like a million times computationally expensive than the initial problem, which makes it impossible to be running using a computer, even with a supercomputer most of the cases, uh, when you add more and more dimensions into your problem, right? So that is why we are going to so this happens if you have to calculate these new variables one by one for each data point, right? But instead of calculating each of these new variables, right, x3 variables, x4 and so x5 and so on, where we have to calculate the coordinates in the high dimensions for all these data points uh, with all the dimensions. Uh, this kernel trick can be used to convert get the benefit of converting into higher dimensions without actually transforming these dimensions into higher dimensions uh, with calculations, right? That means you don't have to really calculate these new variables, but using this kernel trick, you can internally, right? Uh, you internally it would be converted into multiple dimensions, and the classification would happen without actually converting these variables, number of variables into higher dimensions. So that is the idea of using kernel trick, right? So when we are using kernel trick, what we are doing is we are trying to uh, we are trying to get the distance between each of the data points, right? And you can use the kernel trick, right? So if you want to understand it in a different way, right? So when it comes to finding the uh, multidimensional values, what we really want is to find the distances in the high dimensional vector space between each of these data points, right? In other words, when it comes to data points that are in a certain dimensions, uh, if we have the distances in between each of these data points for all the with respect to multidimensional vector spaces as well, still you can do this apply this optimization problem and use the linear separability and linear separate these two classes without actually converting this number of dimensions into higher number of dimensions, right? So, so before we learn about how to apply this kernel trick, we have to know what is the kernel function is, right? The kernel function is actually a measure of distance between two data points in a vector space, right? Say like this is the this is a two dimensional vector space, and this is one data point and this is another data point. So the distance between these data points can be measured, right? So, and when there are three dimensions also, these two data points uh, distance can be measured in a different way, right? So if we can calculate the distances between these two data points, even with multiple number of dimensions as well, then we can use these distance values for multiple dimensions and apply it into our uh, optimization problem, and you can get the effect of linear separability, and then you can solve the problem, right? So in order to find the distance between two different data points, you can use a function known as the kernel function, right? This kernel function should be having some mathematical requirement known as the positive definite. We are not going to discuss it in this lesson, right? So when you are having a distance measure satisfying this uh, positive definite requirement, it would be known as a kernel function, right? How to find this, for example, if this is x value, x data point, and this is y data point. So distance between x and y can be measured in different ways, right? So there are some of the examples of measuring the distance between x and y, right? The simplest form is known as the linear kernel. So the distance between x and y can be represented as kxy, or the kernel function of x and y, simply using this one, right? X transpose y. So this is the simplest dot product of two vectors, right? If you take the x vector and y vector with same sizes, you can take the dot product of these two vectors and find uh, the similarity of these two vectors, right? So it is also a measure of this distance, right? In this case, you can see that there is no higher order polynomial is used in x, but simply the same x, the same y are used in the used as the parameters, and they are used to calculate the distance between these two x and y vectors, right? And also there can be polynomial kernels where you can use uh, polynomial kernels, something like this, right? So this is a generic form of polynomial kernel where x transpose y plus r to the power n. This r can be a scalar value, which is a positive value, right? Positive or zero value, and this n can be a number which is equal or greater than 1, right? When you are using this kind of polynomial kernel, you can have not only the exact x and y values dimensions, but you can use the polynomials of these x and y variables to calculate this distance, right? So in this case, we are using these x and y values, linear values, that means the same dimensions to calculate this distance. But when it comes to polynomial kernel, depending on the values of n, you can have uh, higher order distances, right? It's like if we had 5 dimensions, what would be the distance between these two data points, something like that, right? Uh, and when it comes to Gaussian kernel, or known as the radial basis function, uh, this is also another form of kernel function. It can be represented like this, right? Where sigma is greater than 0. Sometimes this 2 sigma square is considered as 1, right? So for some representations, right? But sometimes this sigma can have a different value, so that it can also be tuned, right? Uh, and sometimes this 2 sigma square is converted into is taken as a different value, right? So we will see it later, right? So as a gamma value, right? In this case, this Gaussian kernel or the radial basis function, there are infinite number of uh, dimensions, or it can be a polynomial of infinite dimensions. Not it can be, it is a infinite dimensional polynomial when it comes to when we use this kernel function, right? So this is a very widely used kernel function in support vector machines, right? First, look at let's see about the linear kernels. When it comes to the linear kernels, we just use the inner product or the dot product of two vectors in the same vector space, right? Like I explained earlier, right? Uh, Linear kernels does not change the number of dimensions, as I mentioned earlier. We are not taking uh, any uh, any nth order power or square or cube or something like that of these vectors or the dimensions when we calculate the distance between these two vectors, right? So this is an example for that. If X is X1, X2 transpose, and so transpose means this should be ordered like this, right? X1 and X2. That is why I explained it as transpose, right? Similarly, this should be Y1, Y2, right? Y vector. And when you take this linear kernel, uh, this dot product is taken, or this X transpose Y is taken, then the value would be X1, Y1, X2, Y2, right? When you multiply these two values, X transpose T, when you X transpose Y, this would be the value, right? There are no higher order polynomials in this linear kernel. So this is the simplest form of kernel that can be used for as a kernel function, right? In the original form of dual problem, we can see this linear kernel is already there, right? So we will see how we are going to replace this linear kernel with higher order kernel so that we can have linear separability in higher dimensions in the dual problem. And not like the linear kernel, the polynomial kernel has higher degrees, right? Higher degree polynomials up to the degree of function, right? Up to the degree of function means this n value, right? For example, if r is 0, r means, so if you can't remember this value, I'm talking about this value, right? This is the polynomial kernel. If this I said this r is a linear, is a scalar value, right? N is a number, right? If r is 0, that means there is no linear value, this scalar value, you would have only this value as the polynomial kernel, where you are using this same linear kernel and take the nth power, right? N is 1, it's just this linear kernel, right? So this decision boundary would be a linear decision boundary as usual, right? If n is 2, it becomes a quadratic kernel. That means the decision boundary would be a quadratic decision boundary, right? When n is 2. When you take n as 2, you can actually calculate, right? So if you take like, so if I said when you take the linear kernel, if the xty is x1 y1 plus x2 y2, right? This is the dot product of, or the inner product of x and y, right? So when you take the square, when you take the quadratic of it, you can get the square of these two terms as well, right? Then it would be like x1 square y1 square times x2 square y2 square x2 square y2 square plus 2 x1 y1 x2 y2, right? So then this would be a higher order polynomial. Similarly, by increasing the number of dimensions or changing the number of n, you can increase the polynomial that is used in this kernel, right? And when you increase it into 3, it would be a cubic decision boundary, because this would be having cubic terms, right? x1 cube, y1 cubes, and so on, right? Similarly, you can increase the n number, and you can increase the polynomial, the degree of polynomial that is used, right? So that is when we are using when r is 0. By increasing the r, which is scalar value, you can actually shift the decision boundary along the Cartesian space, right? So we are not going to explain it in detail, but that is how it happens. So this is the most important kernel function that is practically used in support vector machines, which is known as the radial basis function, known as RBF. Which is also the simple notation is RBF, or radial basis functions, right? Is also known as Gaussian kernel, right? Unlike the polynomial kernel, where we have to decide the value for n naturally, this Gaussian kernel has infinite number of dimensions, right? Because of that, it has very higher nonlinear decision boundaries, right? If the polynomial size is infinite, definitely it would have higher nonlinear decision boundaries, right? So it can be represented as like this as well, right? So in the earlier case, let's move to the original notation, right? So we take, when it comes to Gaussian kernel, it would be represented as e to the power minus x minus 1 norm square divided by 2 sigma square, right? Sigma is a positive value, right? And sometimes this can be 1 or something, or this negative 1 over 2 sigma square can be represented as minus gamma as well, right? So this gamma can be tuned so that it can tune the bias variance trade-off, right? So with lower gamma, we can have a smoother hyperplane. That means when you have some data points, this smaller gamma would have very smooth hyperplanes, like let me take another color. This would be a very smoother hyperplane with low gamma, right? It would be having a higher bias because this decision boundary is not complex, but because it is simpler, the variance would be lower, right? But with high gamma, it would be having a much wiggly, that means a much complex decision boundary like this one, which would be having less bias. That means all the data points can be correctly classified, but this may, when the real world data are used in this model, there would be higher number of errors. That means this would be higher in variance, right? So you can find the best gamma value using the cross validation, right? Okay, and so now what we can do? So this is the dual problem, right? So the one we explained it earlier, right? This is the exact dual problem which we are going to optimize. Not the dual problem, actually. This is the statement that we are going to optimize, right? And in this optimization statement, there is this xi transpose xj statement, right? So this is similar to the linear kernel, right? So what we are going to do is we are going to replace this linear kernel with the higher order kernel, something like the polynomial kernel or the Gaussian or the RBF kernel, right? So this this linear kernel can be replaced by this kernel function, whatever the kernel function that you want. This kernel function can either be a polynomial kernel, it can be a Gaussian kernel or whatever, so that you can have nonlinear decision boundaries, because the actual nonlinear means you internally it is converted into a high dimensional space and then use linear classification, linear separation, right? But in for the outside, what you see is a nonlinear separation, right? So when you want to separate nonlinear, uh, when you want to have a nonlinear classification or nonlinear decision boundary is there, you can use this kind of Gaussian kernels and use this kind of optimization in the dual problem. Actually, when you are implementing it in the real world, you don't have to remember all these things. What you have to know is that whether what is the kernel type that you are going to use, whether it is a linear kernel, polynomial kernel, or a Gaussian kernel, right? So then you don't have to worry about these dual problems and so on with language implementations like Python. You would be simply be able to run this support vector machine so that you can get the values directly, right? So in this case, what we are doing is we are going to replace this linear kernel with whatever the kernel that you want, and then you can run this algorithm so that you can have nonlinear decision boundaries. So once you have found these uh, support vectors, that means once you have found these alpha I values, and once you have this kernel function, then you can have the support vector kernel, support vector machine using the kernel with this formula, right? Where kxi is the kernel function. What if it can be a radial basis function in most of the cases, and these are the Lagrangian multipliers that we learned from the SVM algorithm during the training process, and this is the operation for sum for all the support vectors, right? So this is the final decision making model that was developed using support vector machines, right? So remember, then now this is a classification problem that is binary classification problem actually, that can be solved using the support vector machines. So after learning about this classification problem that you can solve with support vector machines, there's another form of support vector related machine learning algorithm known as support vector regression, right? So in support vector machines, what we are using is we are going to we can do binary classification mainly, and with support vector regression, you can find a certain value, you can predict a certain value using this SVR algorithm, right? It's actually a machine learning algorithm like the other regression algorithms as well, right? The idea of using this support vector regression is to find a function which is also having nonlinear distributions, uh, which can be used with higher success rate, like in the support vector machines, right? Uh, Unlike in the linear regression and logistic regression, with especially in the when it comes to linear regression, we want to have a linear relationship, but when it comes to nonlinear, highly nonlinear datasets, you can data distributions, you can use support vector regression, right? Because in support vector regressions, uh, unlike this ordinary square, right, where you are measuring the distances from all of the data points, and we are trying to optimize this uh, regression line. When it comes to support vector regression, we are having a tube, right? this yellow color path is a tube which is having a epsilon value, or known as the error, right? This is known as the epsilon insensitive tube. Sorry, epsilon insensitive means all the data points that are inside this tube uh, would not be considered as a loss, right? So, and all the data points outside this epsilon uh, insensitive tube would be considered as support vectors, and their distances would be considered when it comes to this optimization. So there are much more into the constraints and so on in this optimization when it comes to support vector regression, but we are not going to discuss it here. What you have to know is that unlike in the linear regressions and so on, when you are having support vector regressions, all the data points that are inside this alpha insensitive tube, which is where the alpha is calculated perpendicular to this axis, right? So this is the epsilon. All the data points that are inside this alpha, sorry, epsilon insensitive tube are considered okay. That means they are not considered for error calculations or loss calculations, and only the data points outside this epsilon insensitive tube would be considered as support vectors, and their errors are calculated using this psi terms and psi star terms, psi asterisk terms, right? And they are optimized using this kind of optimization function, right? We are not going to discuss that much about in this lesson, but this is what it does, right? So why are we using support vector machines? Uh, when it comes to high dimensional spaces, right? For linear separability, support vector machines are best, right? That means when it comes to linear regression and so on, we can use polynomial regression and so on, but this support vector machines are very special, right? So we can use very high number of dimensions, like the radial basis function with infinite number of dimensions for, and then do the uh, linear separable, then you can achieve the linear separability, right? So because of that, these SVMs are very much successful in these kind of scenarios. So that means when you increase the number of dimensions, that means you are increasing the number of features, right? When you increase the number of dimensions, means you are increasing the number of features. When you increase the number of features to a very higher number, uh, in order theory that as we know, right? So we can't have higher number of dimensions more than the number of data points, right? When it comes to a problem like linear regression, then the problem, these conditions would not be satisfied when the number of dimensions are higher than the number of data points. But with support vector machines, you can achieve it, right? Can achieve very large number of features in multiple dimensions for a limited number of data points, and do the support vector machine or support vector regression and optimize, right? And support vector machines are actually, so because of that reason, you can use support vector machines for image recognition, bioinformatics, and text classification problems, right? So in that means in the before the deep learning came into the scene, support vector machines were one of the most widely used technique for these kind of purposes, like image recognition and text classification and so on. And these support vector machines are best used when there is a clear margin separation between the classes, right? Unlike in the logistic regression, where you are having higher, you can deal with higher amount of that means intersection between different classes. When it comes to support vector machines, we are assuming that there's a clear separation between the classes, right? So that is one of the main assumptions that you uh, have to make when you are going to use support vector machines, right? And as we said that SVMs are can be it's mainly used when you want to use uh, kernel functions for nonlinear classification. Right? That means when you have a very complex data sets, where the decision boundaries are very complex, you can use support vector machines. So that means when it comes to natural data sets, like as I said, the text and images, these kind of support vector machines can be used uh, with higher accuracy, especially before the deep learning was used. So when you are using deep learning, you need a lot of data, but when it comes to support vector machines, with limited amount of data, you can do it, right? And when it comes to support vector machines, the other difference from support vector machines and the deep learning or deep neural networks is that deep neural networks are generally used for large amount of data. Right? But when it comes to support vector machines, when the number of data points are increasing, uh, the optimization calculations are becoming exponentially, uh, not exponentially, but quadratically, uh, making it expensive, right? Because of that, when you have a large amount of data, it is not advisable to use support vector machines. Maybe you can move to some other technique like deep learning. But when it comes to limited amount of data, like we had in the earlier days of machine learning, support vector machines were very useful. And you can use the C parameter for regularization for overfitting, right? And when the dimensionality is high, you can use different values, right? And you can tune the radial basis function as well, right? And also when it comes to support vector machines, they are inherently binary classifiers, right? As I said that unlike the logistic regression and softmax classifiers, these support vector because they are binary classifiers, when these kind of problems are there, you can use it. But when there are multi-class classification problems, support vector machines can still use using one versus all and one versus one strategies. So this is all for the today's lesson. If you have any questions, you can ask.